Alright, it's demo time for day one, and now we're building a simple movie search system for science fiction movies that basically works in a way that we send it a query like Alien Invasion, and it retrieves back the most similar movie in my database to it. So we're basically also experimenting with the chunking methods that we just discussed in the last video and using Hugging Face for our embedding generation. Let's get started by just installing our dependencies here. And here we're having sentence transformers, which is the library that we're going to use by Hugging Face for our text embeddings. Those are the embeddings that we're going to use to generate the embeddings for our documents, the ones that will go into our database. Right, and then transformers, which we're going to use to analyze the token count of our documents, Qdrant client for the Python client of Qdrant, and also a few lemma index dependencies that we're going to use for our chunking. So when we get there, I will explain a bit better, but basically it's going to help us with the chunking methods that we're going to be applying and giving us the methods that we need to make things easier for us. Here we're using the sentence splitter and the semantic splitter node parser specifically by lemma index for that, and also the Hugging Face embeddings, which is the library that we need to help the semantic splitter to analyze the chunks and split it semantically, right? So we're importing that, and after that we are initializing our text encoder, basically the model that we're going to use by sentence transformers to create our embeddings. So we run that, and the model that we're choosing here is the All-Mini-LM L6v2. This is a very popular model, and it produces 384 dimensional embeddings. And this is different from the amount of token limit it has, which is 256. That actually means that this model can handle up to 256 tokens per input. So I want to chunk my data if it goes over that limit so I don't lose any meaning, because this embedding model is based for 256 tokens. So if we want to check if our data passed that limit, we're going to have to use a tokenizer. And as we can see here below, we have the data set that we're going to be working with. This is our movie data set. It has around 15 science fiction movies. And here we have a few informations like name, description, author, and year. Now, the thing that we're going to want to embed is obviously the description, because it is a place that has the most information about our movie that we want to create our embeddings from. But we can see here that these descriptions, some of them are very long, most of them are very, very long. So most likely they are going to exceed the token limit of my embedding model. I specifically did this so we could use chunking methods, right? So let's see by how much those descriptions actually exceed the limit of our embedding model by using this auto tokenizer by transformers. Now we are using the same tokenizer that our encoder, which is All-Mini-LM L6v2, is using to accurately generate and predict where should we split our chunks, right? And here, if we run that, we're going to see that basically almost every movie except from Arrival exceeds the token limit. We can see here, for example, Ex Machina has 386 total tokens and exceeds the limit by 130 tokens. That means that we can create one chunk that's 256 tokens and another chunk that is 130 tokens, for example. Now, next up here, we're going to want to just set up Qdrant. Since this is a very small data set, we are just using the Qdrant in memory mode. This means that the data is only stored temporarily on RAM. We're not going to have to connect to anything outside of our system, but also that this memory is not persistent. And this is only good for demo and very small use cases. But this is what we have here, so we're going to be using that. The collection name is My Movies that we're going to be using. And after that, we go into create and defining the collection that we are using here. The first thing that we do is to check if the collection my movies already exist and delete that just to avoid any conflicts. And then we're going to create this vector config that is basically setting up 3 named vectors. And you can see here that we are setting 1 name vector for each type of chunking method that we are using. And for example, if I have chunks that I created using fixed size chunking, then I'm going to add this to this named vector right here. This is basically for us a way for us to experiment with named vectors. And we're also using the same distance metric to compare all of them inside, which is cosine similarity, right? So let's move forward and actually get into the implementing of our text chunks. And here we are setting the token limit that we discussed earlier. 256 is the maximum that we can have here. And we are defining 3 functions for each one of the methods that we're going to be using. So fixed size chunks, sentence splitter, semantic splitter. For sentence splitter and semantic splitter, like we mentioned before, we are using lemma index to help us with that. So sentence splitter, we are using the sentence splitter method by lemma index, setting the chunk size to our limit. We can just do this right here. And having a chunk overlap of 40. For the semantic splitter, we are using the Hugging Face embedding that's going to define the model that we're going to use to define the semantic splitting. And we're using the same model that we're using for the encoder here. If you want to learn more about these parameters and what they do and how to work with these methods in lemma index, we're going to have the link for them in the description below as well. So chunking strategies, I'm not going to go into them specifically because we already covered that in the last video, but there is a quick overview here of each one of them and what they do and how they do it, right? After that, we are going to get into the chunk embedding and uploading of our data itself. Here in this cell, we are, for each one of our movies in our documents, right? For each doc in documents, we are getting the description and chunking in different methods, right? Then we're getting those chunks and embedding them and uploading it to our vector database in the specific vector field that we define for them, right? We're also using a payload of chunking with the method alongside that we use for the chunking as well. And along with it in the payload, we're adding the whole movie information in this doc here, which is basically the information that we defined here. This whole thing is getting in there. So year, author, the entire description of the movie, and also the name. We're also adding the chunk itself that was used for that embedding and uploading all that to our collection. So let's run that and see how many vectors we have in total. Oh, I got name. Oh, I forgot to run this out right here. Let's do that and try this again. And then let's see how many vectors we have in total after all the chunkings and all the uploadings. Now, this takes a little bit of time, mostly because of the embedding generation that can take a little bit of time as well, and also because of the semantic splitter that is using also an embedding model to generate the semantics and split our chunks. We're also using the method upload points to basically upload all of these points to Qdrant in a very efficient way. So here you have uploaded 82 vectors to Qdrant. So all these methods generated 82 vectors. And now it's time to run our semantic search query to find the closest vector in our collection to our query alien evasion, like we mentioned earlier. And for that, we need to also choose our chunky method, the chunky method that we want to use for that. In this one, we're using the fixed method just to try it out with a limit of 3. So we want 3 results, and we can just start by running that. The query points method is going to return us something like this, which is a little bit unreadable if you don't want to keep scrolling. So let's try to put this in a little bit more readable way, and then we can see first is annihilation with a score of 0.45, then AT, then arrival. Very cool. Now let's try to define a query helper function so we can basically search with multiple chunking strategies and see what are our results, right? So let's define that. And now we can see a little bit better and compare better what are the results that we're getting. We can already see here that searching alien invasion with the semantic chunking give us a different top K order than using the fixed chunking. After that, it's time to inspect. Like, since we have different orders and our chunking methods are giving me different results, then let's see what are the chunks that's being retrieved in each one of these points. And let's try to compare if it actually makes a difference between splitting in a fixed size or sentence size or semantic in our chunks, right? So let's define a function to do that for us. And let's try to search through all of our chunking methods using the query alien invasion, right? So let's get the results for all of that. And now we can see all chunks that are being retrieved with our results. Now, let's take some time to quickly analyze these chunks and what they actually look like. We can see here that for fixed size chunking, the first chunk here is already starting in the middle of a sentence. So it starts with a comma and goes into making the journey a symbolic mirror of their inner decay. This is clearly mid-thought, and this is one of the downsides of using fixed size chunking. Even though that happens, annihilation is still the first result for all three methods, which is a good indicator in general. Then we can see the sentence type chunking. Now we can definitely see the difference right here. Now this is definitely full sentences. Things make just a little bit more sense in general, but as our data grows bigger, if you're looking for example, a book of 200 pages, you're gonna notice this difference much more clearly. After that, we have semantic chunking, and we can see here that the chunk for annihilation is just different from the one from sentence chunking, even though they are just similar in general. We can see here, this is the same chunk of sorts, right? But still, this one for annihilation is a little bit different. So we have here, each character is marked by loss of self-harm, making the journey a symbolic mirror of their inner decay. Now, this is a very interesting sentence, and it does make more sense to start with that than to start with the film's nonlinear narrative and haunting imagery evoke themes of trauma, memory, and blurred line between adaptation and annihilation. Even though this is a full sentence, it feels like it's starting in the middle of another thought that was initiating the sentence, right? And this one feels just a little bit more like it's the beginning of a sentence itself. Those are subtle things, but they can really improve the precision of your retrieval, especially if you're looking to smaller chunks. For example, if we wanted to create chunks that are just, I don't know, 40 tokens, we can do that really quickly. Here to see if the difference is a little bit higher. So let's try to change this max tokens here to 40. Create a new collection, change max tokens to 40. Upload the points again. We're going to have more points right now because we're going to have more chunks, right? And then we can see how much our queries differ from doing that. We have now 409 vectors with the token size limit of 40. It took a little bit more time to run this out now because of especially the semantic chunking takes a little bit more time to run. And this is one of the downsides, even though it's more semantically aligned and has more precision and so on. But here we can see the search results being performed again, and we can now see different orders for our results, right? Now annihilation is second for fixed size chunking. And let's see how this impacted our queries overall, right? Let's try to run these cells again, see what happens. And we can see that for semantic, annihilation is still the first one. So let's try to see here this result again, right? For fixed site chunking, now we have a different sort of result. We have a chunk that's much smaller here, and we can now clearly see that this is the middle of a thought, right? And it also ends in the middle of a thought as well. Same thing here, and same thing here. We can see this much more clearly. For sentence chunking, we can see here that things is starting to get a little bit weird, but not so much, right? We can see here it also ends at the end of a full sentence, all three results. Now we can see here that for semantic chunking, it's basically the same. And the reason for that is because our max token count doesn't really affect our semantic chunking. This is defined by the semantic splitter function itself using here it is, the embedding model, Hugging Face embedding model, sentence transformers, all mini LM L6v2. This is what defines basically where our chunk will be split so that it also fits the context size of this model perfectly and it makes sense semantically. So we have here different results for both of these. ET now appears in the first place. And for semantic alien invasion, we have here ET in the third place. If you've watched any of these movies, you're gonna see that ET is not really a movie about alien invasion, even though it's a story of ET living and being on Earth. It's not really an invasion per se. And here we can see that Annihilation is the one that makes a little bit more sense to be retrieved first. So we can clearly see with 40 tokens that semantic chunking works the best way. However, if we use the full 256 tokens, we can see that the other chunking methods are actually closer to having this first place correct, right? So it's a little bit of a nuance there when you are choosing all of these things, token limits and so on. So you definitely want to experiment a little bit before you get your search system out in production and make sure that you're optimizing for the results that you want, right? Next step here that we're going to try out is to apply a filter. For example, if I only want movies that are made in years greater or equal to 2000, and we can apply this filter condition here with the key being year and the range being greater than 2000 or equal. The limit that we're going to set here is 4, and let's see what we have here. We have 4 results: Annihilation, Arrival, Interstellar, and then Arrival again. An interesting thing here is that Arrival is retrieved back twice. One, because one chunk had this score and another chunk had this score. Since I'm retrieving by chunk, Qdrant is only taking into consideration the scores of the chunks and retrieving that back to me. But what if I only want one chunk to be considered per movie? For example, the highest scoring one. I only want different movies to be retrieved back to me here. I don't want Arrival to appear twice, for example. So then we can use the method query points groups in Qdrant to do that for us. Here we are using group by and selecting the field name and setting the group size to 1. And that means that I only want maximum 1 result per field name, right? So if I run this, I can see that I now have in 4th place Gravity, and Arrival here only appears once with the highest score that it had. So now I have the top 4 movies that match my query Alien Invasion instead of the top 4 chunks that match my query Alien Invasion based on the results retrieved back here, which is a very interesting thing to have, especially if you're trying to rank, for example, into a movie recommendation system. You don't want movies there appearing twice just because it matches more than one thing within that. You only want that to appear once. So this is very useful when you're dealing with those types of systems. To wrap up day 1, your pit stop project is to create a simple search engine that applies all these things that we just saw. Pick a dataset of your choice, the embedding model from Hugging Face that you would like, a chunking method of your choice. Obviously, you can always use this notebook as a guide, and try to upload that to your database using filtering methods and also grouping by, and see the results that you get. This is a very huge step into your search journey. And as we move forward, we're going to see how to scale that beyond simple small data sets into millions and millions of vectors. Now for day 2, we're going to get into HNSW indexing and how it really works behind the scenes. Why is it important to set up your payload indexes, and also how to tune your HNSW parameters to balance search speed with accuracy and memory usage, and a lot more things that you can do with your HNSW indexing to improve your indexing speed, which is a very, very important part to settle the foundation for what's coming next. So see you in day 2.